Okay. So today we'll speak about models. There's a bit of overlap with the Coco lecture last week. Sorry, the Coco seminar. But here we'll go deeper and let's say not only apply to science, but say to the way we describe our world. And I think it's important to have, let's say, a lecture on this topic because otherwise, we might start discussing about what is complexity and what's complex systems and what's emergence and what's self-organization. But when we will discuss all these topics, we need to be aware about how we are making these descriptions and how we get to know our world. So that's why we need this short discussion on epistemology, and it's related to the papers we read last week. Um, so i- just as a reminder, last week we saw like a brief prehistory of complexity. And are there any questions, doubts, commentaries, comments? Um, so we saw that, let's say, since ancient times, people have been concerned with similar topics and with similar concepts, but only recently is that we have the proper tools to study complex systems, namely computers. And this puts us in a, let's say, privileged position in history because only now we are able to study phenomena for which before we didn't have the capacity to simply describe or observe. So this also already gives us an idea of how we understand phenomena in the sense that we need to make observations. And today we will speak about models, and not precisely this type of models, but let's say descriptions we use to describe the world. But there's this famous phrase by George Box: all models are wrong, but some are useful, especially in engineering, in the sense that there's no, it's inaccurate to speak about the truth of a model, because by definition, a model is a simplification of phenomena. And that's why the criterion according to Box for whether a model is good or bad is whether it's useful or not. So it's rather pragmatic rather than fundamental, in the sense that there would be one true description of the world. And I mean, going a bit back into philosophy 101, in Plato's myth of the cave, there's this idea that basically there's a real world, and then we are just looking the shadows, but then philosophers look at the real world outside the cave in Technicolor, and then they will tell the truth to all the ignorants that are still inside of the cave and don't want to listen to them. And that's why philosophers should govern the city. Yeah, that was his speech. Um, but let's say Plato, and because of that, it's known as Platonism, assumes that there is one single description of the world, and a true description of the world, and that means that all the rest are wrong. And that has led to conflicts throughout history. People argue for truth of something when they don't accept that they simply might have different opinions. So it's like there's this Russian joke that bearded professor comes to class, and one of the students, "Oh, professor, do you sleep with your beard under the covers or above the covers?" And the professor says, "Oh, I hadn't noticed. I'll tell you tomorrow." And then the next day, the professor comes with black eyes under his eyes, and he says, "Well, neither under the covers nor above the covers," because he just started putting attention and well. Um, so it's a caricature of the scientific methods. So we are taught that, let's say, we first come up with a hypothesis and design experiments, and with those experiments, we test the hypothesis and falsify or validate the hypothesis, and like that we build theories and laws and things like that. In practice, that almost never happens, in the sense that there's lots of serendipity, gut feeling, stubbornness, dogmas, beliefs. So it's, let's say, in practice, it's much more complex than that. But basically, we contrast with experience our descriptions of phenomena, and then we try to use that understanding for different purposes. So this let's say an update of the scientific method, and it's not, let's say, linearly, but in general, we have phenomena that we want to know, observe, control, and then we make measurements or observations, and that gives us data. We analyze that data with different tools, mathematical, statistical, and so on. And that allows us to build models, and then we can generalize those models to have laws. That doesn't mean that those laws are truths or immutable. We judge whether these laws are useful if they are helping us understand the models. And then models, we will speak more about them, but let's say some can be for prediction, or for description, or for communication. They have many uses about this data, and then we check the consistency of that data with phenomena. And then all of these can be used to control the phenomena, and that's engineering. And of course, we can also use this control as part of the scientific process, because if we have a model to control some phenomena, and then it turns out that that phenomena doesn't control, it means that we need to revise our model. We'll see more about this type of modeling, and let's say way of doing science by engineering. And let's say models in this sense are used not only in science and engineering. We use them in daily life, because we can say that any representation of our world is a model, basically a simplification to communicate. So let's say when I say that's chair, let's say just the word chair, we can say it's a model of a chair, because it's not the real chair. So I forgot to put the so some of you might know this. I have it here. Belgian painter René Magritte, a surrealist. Yeah. So one of his famous paintings is this. This is not an apple. So it can be seen as a paradox, because you can say, "Oh, but what do you mean that's an apple?" But here it's written it's not an apple. And well, it's not an apple, it's a painting of an apple. But then is it an apple or it's not an apple? And it depends whether the phrase refers to the painting or to the object it's representing, to the signifier or to the symbol. So and he has the same with a pipe. This is not a pipe. Maybe you have seen that one. And of course, this is similar to the liar paradox, that it's simply this phrase is false. So if this phrase is false, then it is true, because it's saying that it's false with Aristotelian logic. And if it's true, then it says that it's false, so then it's false. So it's a paradox. So let's say there are many interesting word games that use, let's say, highlight this distinction between what we observe and how we describe what we observe, or what we want to describe. So let's say, in a sense, this is not an apple, it's a model of an apple. And then if this is not a model of an apple, then we can better understand what's the the phrase referring to. And in one of the papers we discussed last week, Rosenbluth and Wiener wrote that the best material model for a cat is another or perfectly the same cat, meaning that if we want to include all the details of a phenomenon, then we should basically reproduce all its intricacies, but then it becomes very difficult to describe. So the question is which details are relevant? How much of those details do we want to include in our model? And of course, it depends on the purpose of the model. And then we'll see different purposes we can have for models. And Lewis Carroll, who wrote Alice Adventures in Wonderland, but he was also a mathematician and logician. So in his stories, he likes to put paradoxes. And in Sylvia and Bruno concluded, there's this idea of a country that makes maps with more and more detail. So at the end, they decided, well, they wanted to do a map scale 1:1. And then they realized that they could use the country itself as a map. But then if you use the country as a map, it's not very useful for what maps are used. And then Jorge Luis Borges later used the same idea for this short story. That's the whole story. So it's very short. So in that empire, the art of cartography attained such perfection that the map of a single province occupied the entirety of a city, and the map of the empire the entirety of a province. In time, those unconscionable maps no longer satisfied, and the cartographer's skill struck a map of the empire whose size was that of the empire, and which coincided point for point with it. The following generations, who were not so fond of the study of cartography as their forebears had been, saw that the vast map was useless, and not without some pitilessness was it that they delivered it up to the inclemencies of the sun and winters. In the deserts of the West, still today, there are tattered ruins of that map, inhabited by animals and beggars. In all the land, there is no other relic of the disciplines of geography. Suárez Miranda, Viajes de Varones Prudentes, libro 4, capítulo. That's not a Roman number, but anyway. No, yeah, 45. Lerida, 1658. So all of that is made up. But the interesting thing is that the title of this short story is On the Exactitude of Science. And of course, if you read that, it doesn't seem that it has anything to do with science. What you could see, geography, that's science, yes. But it's precisely this idea of the map and the territory, the models and the modeled, and that if we want to put in our models all the details of the phenomena we want to include, those models will be useless because they have not only too much information, but actually infinite information, because for real phenomena, you can always extract more and more information. It will be difficult to claim that a model is complete, no? Because you can have a phenomena and assume that you already describe at the elementary particle level all these details. Well, first of all, like the most sophisticated simulations, I think they can hold like 50 elementary particles interacting, and that's already too much. But let's assume, okay, a model of 2 elementary particles. But then it wouldn't be complete because in reality, those are not isolated. And then when you start including the interactions with other elements that were not in your model is no longer complete. And since you cannot exhaust all possible interactions, just like you cannot pre-list all possible uses of a screwdriver, you cannot have complete models. And that limits them in different ways that science still has to accept, but that's why science is an ongoing process. And Baudrillard, in his Simulacra and Simulation, is more a critic of society, of capitalist society. But it's the same idea. So I mean, Baudrillard he was a philosopher, I believe postmodern. But his book has nothing to do with science, but it's the same idea about how we describe the world and how we perceive it and how we interact with it. So he was saying that modern society, consumer society, sells us lies that we take to be real. And I mean, he's not arguing that there is a real description of reality. It means he's saying that there are some things that are obviously not real, but then we take them as real. And the example he gives is Disneyland, that we know that, let's say, it's made up, but then they made the place and we go and pay money for it and buy merchandising, and it's good business, but it's not something real. And if you know the main idea behind Sapiens by Yuval Harari, he argues that what distinguishes humans from other animals is that we have narratives that can allow us to do things that we normally wouldn't do. So, for example, concepts like moral or religion or economy, money, all of those are not real. They're inventions, but they're agreements. And they allow us to do at the social level many things that normally we wouldn't do. So that's like the big difference with other animals, that they are, let's say, stuck into their habitual behaviors, and yeah, they can do some innovation, but not do at the level that our species has done so far. So if we take that interpretation, then the fact that we are able to do this, it's actually what makes us human. That we kind of can make up things and take them as real. So that ability to use language, to use models in such a way that we don't need a physical object to represent or to stand in for something, but that we can just manipulate symbols, and these symbols can be arbitrary, and the meaning also becomes arbitrary. It's important, let's say, not only for Bitcoin, which is precisely what it is. The value of Bitcoin is arbitrary, but even complex language, well, even simple language is like that. The meaning is also arbitrary. And back to science, introduction to his book, Metaphorical Brain 2, Michael Arby wrote that a model that simply duplicates the brain is no more illuminating than the brain itself. So it's the same idea that if we add all possible details to a model, then it won't be that useful. Let me get this here. And of course, the precise balance of how much we want to include in our model is contextual, because it depends on the purposes of the model, how much detail we need to include in that model. And we'll see more about this now. And John Holland, who, let's say, I forget whether we will read one of his papers. I think we will. But he's, let's say, one of the pioneers of the study of complex systems. I think it's attributed to him to coin the term complex adaptive systems, and also he proposed genetic algorithms back in the day. So I'll just read the quote. Modeling, it should be clear, is an art form. It depends on the experience and taste of the modeler. In this, it is much like cartooning, especially political cartooning. The modeler, cartoonist, must decide which features to make salient, exaggerate, and which features to eliminate, avoid in order to answer the questions, make the political point. So here it's very clear that it's not about truth. It's something because, of course, political cartooning is not about truth. It's that you want to exaggerate something to be highlighted. And of course, depending on whether you are right-wing or left-wing cartoonist and you are portraying a right-wing or left-wing politician, you will highlight different aspects of the politician that you are cartooning. So it is the same with models. So, I mean, all of this just to stress that there won't be a single model that will be good in all contexts. And then we can classify different types of model depending on the substrates, basically on how they're built. So, for example, if we build a little catapult, that's a material model of a big catapult, or a little car or a little train. That can be useful because it's cheaper than making a big one, and then we can scale test one idea if it works. Or now with 3D printing, let's say we can have an idea, 3D print it, and then kind of check whether it works or not. In biology, organisms can be models of other. So, I mean, it's like a different use of the word model, but the model organisms like C. elegans, E. coli, mice, the fruit fly. They're animals that have been very well studied. And for example, the mice, the knockout gene mice, they basically remove all their immune system. So then they can be used to test different biological situations like cancer, different types of cancer, and then remedies against cancer in a living system. So it's a model because it's not taking humans with cancer and making tests on them, which would be the real thing. But let's say a biological replacement or substrate, which in a way it's simplified because it doesn't have immune system, short lifespan, cheaper, and so on. But you can test some biological processes. And this would be at the same time natural and incomplete because, let's say, we are building and manipulating the real world, but since these are also in the real world, then we don't have a complete description of those models. And then those that we build, not physically, but let's say formally, can say that they are complete because we have like a full description of the model. That doesn't mean that the model describes completely the model. That, as I mentioned, it cannot be possible. But then we can have formal models like cellular automata that we will see in the next 2 weeks, which basically based on mathematics or logic. We can have computer simulations or just theoretical models and more. Yeah, so the difference between complete and incomplete is that we are the ones defining the complete models. So our definition is complete. And incomplete, it's more that we have a description of them, but we don't have a full description of them. So of course, it's easier to replicate the complete ones because we have the full descriptions. And again, the question how sophisticated the models should be, how much do we want to, it depends on how much do we want to predict or explain or explore or generate. And then we'll see that this will depend also on the scale at which we are interested in describing a phenomenon or the scales, because we can have, let's say, a model of a cell in its molecular richness. So then we are describing all the molecules interacting, chemical reactions, and then it's like we need supercomputer and it will take weeks or months to run just a few reactions. And then imagine to replicate that for a brain with 10 to the 11 neurons, or yeah, and 10 to the 14 synapses. But then we might be interested more about morphogenesis or just some aspects of tissue, and then we can simplify, and the model of a cell could be simply a Boolean variable: 0, it's dead; 1, it's alive, and that's it. So if we go to a lower scale, we usually require more and more information because everything is different and unique. And when we go to higher scales, we start erasing distinctions, and we need basically no information, or less and less information as we go to higher scales, because let's say since there are less distinctions, we are already including everything in our description. So we need less information to differentiate different states. Whereas when we go to very particular, we end up with, in practice, infinite information because every state is unique, and nothing repeats. Nothing will be repeated. So that's another limitation of highly detailed models. That, let's say, now with the availability of large amounts of data, that I don't know how's the tendency now, but for some time, the amount of data that our civilization had produced was duplicating every 2 years. So I don't know, assuming that tendency still continues, which maybe it isn't. So yeah, I'll use a previous year. So, for example, the amount of information that we generated between 2011 and 2012 was equivalent to the amount of information from the origins of writing to 2010. So that's like a huge increase of data that we've had just this century, and by orders of magnitude. But then having so much data, it's very tempting to have highly detailed models that include all that data, and especially in AI, it's like, okay, we'll train with all of the internet, and then we'll generate artificial internets of LLMs interacting each other and publishing posts, and then we'll train more LLMs with that data. So it becomes very tempting, but the problem is that when you have so much data, then nothing will be repeated, because the more variables you have, your data sets become more and more sparse. So yeah, I won't go deeper in that direction, but there's much to say about the effects of having lots of data. It has advantages and disadvantages. So depending on our purposes, Bruce Edmonds and collaborators list these 7. In many cases, people assume that models are for prediction, and well, some models are for prediction. And in that case, we usually need real data to contrast models or to calibrate parameters, and then we'll be able to predict more or less. And some people like Maxis and Miguel make distinction between prediction and forecast. When you hear those two words, what do you think is the difference between prediction and forecast? Weather prediction, forecast prediction.
Forecast is checking the well.
Sorry.
Yes, forecast would be studying the pattern of how it's been so far. Maybe like plotting a graph where you put the points of how the trajectory is, and then you try to understand that it's going to appear next. But prediction, on the other hand, is more like considers the variables at a given moment and tries to anticipate what is the outcome based on. That's my interpretation.
Yeah. There are many interpretations. And anybody else? Yeah.
as you mentioned, like forecast requires historical data, while prediction doesn't require it. It just needs some inputs, input data. It can be structured, it can be unstructured.
Mm. Anybody else? So, yep.
Prediction is more validated without forecasting, which is very small, quantitative because it requires statistics.
Mm. Maybe.
I said the forecasting is more statistical, so it can be categorized as not competency.
Yeah, maybe I'm mistaken, but the distinction I had of those is that prediction should be more precise, and forecasting should be, let's say, has more margin of error. Because in weather forecasts, let's say you say, oh, there's I don't know, 30% chance of snow in the next 2 hours. So that kind of gives you a margin of error. And prediction basically says, oh, at 11:26 in Vestal Parkway and Bonny Hill Road, there will be, I don't know, this amount of wind, this amount of precipitation, this type of snow. But maybe I'm mistaken.
Forecast. Because forecasting is about learning historical patterns and applying what we saw in the last few years.
Mm-hmm.
My prediction is it's not learning. Whatever you give, and based on such assumptions and what the input data
Mm-hmm.
it just gives you.
Yeah. So the bar for prediction usually is much higher than for forecasting because and for example, for weather forecasting, if you say, oh, tomorrow will be the same weather as today, you already have 50% right. Simply because there's some histories and doesn't change randomly. But then when you want to improve it and turn it into prediction, then it's not possible because of its chaotic nature. But then let's say in many cases, when we say that prediction is limited, it might say, well, yes, it's limited, but then we have forecasting, and then that should be strived for. But then it also depends on which margins do you have, because let's say stock market is notoriously difficult to predict, but then you can forecast and make fortunes just by guessing 1% over random behavior. So, yep. Okay, so other models are used for explanation. So these have to do more with causality. And I mean, there's lots of problems with causality because, again, well, we'll discuss it next class when we speak about emergence. Yeah, because it's tightly linked with the idea of causality. And as we will see, it has also at the end, it's also related with epistemology on how we describe phenomena. Let's say how objective causality is, how much it depends on the observer, and how much it depends also emergence. How much does it depend on the observer or not? We can have models just for describing phenomena, for exploring theories, for illustration, or basically to communicate, for an analogy, and for social learning. So I forget, where did Turing wrote this, in which article? But this already tells, well, you might have noticed that in physics there are many non-disciplines. So there's, well, not disciplines, concepts. So the quantum mechanics, there's non-locality, well, there are many things that are known. and nonlinearity, it's a big thing in mathematics. So anybody knows what's the difference between linear and nonlinear?
Former mathematical technique.
Could you please throw the mic? Yeah, it comes from mathematics, but yeah.
I'd say first one.
Oh yeah, better say it first. Yeah.
So non.
Well, you can make a line and it's continuous sequence of numbers, but it's linear. So I think that's the difference between continuous and discrete. That's a different difference. Yeah.
But something that we can predict that's non-linear equation predict is that we can.
There, you want nonlinear versus linear?
You want to say first, something first? Okay. I mean, just from a mathematical point of view, I guess linear means like any system satisfy scalar multiplication and then addition.
Yes.
Then that's linear. Otherwise, this is not.
Yes. But do you know where the name comes from? Why it's called linear?
No.
So
That's probably because there's no first order, what was that called? Like ax plus b, and then there's a linear graph, so that's called linear.
yes. So in classes of analytical geometry, we are taught the equations of straight lines, and it's basically y equals y minus x1 or something like that. So basically, if you have 2 points, you can have the equation of the line. And that's linear because the variables x and y don't have exponents. Or if you have 1 point and the steepness, you call it in English? Yeah, it's
slope.
Slope, yes. So with either 2 points or 1 point on the slope, you can define a line, and the equation of the line, it's linear because it doesn't have exponents. Now, a parabola, it's nonlinear because it has exponents too, like y equals x squared. And what you said is that if you have a linear equation, basically without exponents, when you move a bit in x, you move proportionally in y. It doesn't need to be the same. I mean, if the slope is 1, then it's the same. But let's say if it's higher, then you move a bit in x and you move up a lot in y. But you move twice in x and you move twice in y, no? Because it's a line. And if the slope is very slow, it's the other. You need to move a lot in x to move a bit in y. Now, if you have a nonlinear equation, you don't have those proportionality effects. So you can move a lot in x and then you move little in y, but then the curve changes and the slope changes and the behavior changes. So that's why it's difficult to predict, because in a linear equation, you can extrapolate to infinite. In a nonlinear, if you don't have the precise equation, and since the thing with complexity is that when you have elements interacting, if you have a system and you have lots of elements, if they are not interacting or they have weak interactions, So you can describe those as linear because basically what happens here might affect others, but not too much, or it affects us in the same way. But then when you have slightly strong interactions, then those interactions become multiplicative, and then they're nonlinear. So you have like cascading effects, and then that limits prediction. Yeah.
How acceptable is this statement?
Uh,
From your point of view?
well, yeah, we should go into the context in which Turing wrote it, because I could say that there's also nonlinear prediction and there's also linear description. So
Because this is in a sense challenging the things we have learned thus far about complex systems. The predictions are like linear.
well, what I'm trying to convince you is that in complexity, prediction is limited precisely because of nonlinearity. So let's say if you have a description of a phenomenon, and let's say you already experiment, let's say have enough data, and then you can fit a nonlinear curve, then there you can make prediction. But then you don't know outside that area that you explored how it will extrapolate. So let's say if you have endpoints, there's a single polynomial of degree n that will go through all those points. But there's an infinite number of polynomials of degree n plus 1 that will go precisely through all of those points. So most probably, if you have a model that fits all of those points, it's one of many that goes through all of those points. So that's what happens with neural networks that overfit the data, that they fit that data, but then they are unable to extrapolate. Or yeah. So yeah, I would say that prediction is limited, and if you have linear models, then you can extrapolate till infinite. But yeah, I wouldn't agree completely with this phrase. First, because there's non-linear prediction, and then because in many cases, linear models are not sufficient for prediction. So yeah. Okay, well, that's a pixelized image. Yeah, it's from last century. So we can describe the inductive method that's used by formal and computational models, that we observe facts and then we generalize or abstract a theory. And this more or less what I described earlier. And then we predict some facts, which, let's say, again, this would be like phenomena. And then we verify, and this is more phenomena, and then we falsify and justify the theory. So this is like the classic scientific method. So it's basically developing theory by induction, observing, generalizing, verifying, and also through prediction. But of course, this would be a predictive theory, and then we know here could be also description, and then instead of verification would be whether we understand, and then whether this basically helps us understand the theory, or let's say we can falsify it in that way. And then the synthetic method, which, let's say, we can say, well, there's this book by Herbert Simon, The Sciences of the Artificial. And of course, he refers to artificial intelligence. He was one of the founders of artificial intelligence 70 years ago. But well, Simon, in his book, he speaks more about complexity than about artificial intelligence. But let's say the models that we basically build, either material or computational, basically we observe phenomena, we generalize for to have theory, but then we build a system, artificial system, which could be, let's say, as I mentioned, a toy catapult or a robot, and then we operate that system, we observe performance, and that helps us falsify or justify the theory. So for example, if we have a theory of how fish swim, then with the inductive method, we can have this theory, and then we predict like, oh, let's say it should have these properties, like, I don't know, the proportion of the fins or whatever. And then we observe and measure the fins and the muscles or something, and then it's okay, verifies the theory. And then in the synthetic method, we basically build a robot fish. And then if we observe the fish and if it behaves similar to the real fish, then it helps justify the theory. Again, since this artificial system can be a black box, it doesn't mean that the mechanism used to build artificial system is the same used by the phenomena, by the real thing. It just means that we are understanding something about it, maybe. Because of course, there might be many different mechanisms that produce the same behavior. So some colleagues have described this as opaque thought experiments. So thought experiment is basically we imagine a situation, like probably you know about these trolley problems, no? With autonomous vehicles, they became very popular.
In one track, we have one people, and on the alternative track, we have 5 people.
Yes. Do you know those dilemmas? You want to explain?
Yeah, so on the original track, we have 5 people behind on the track. And there's a alternative track with only 1 person behind on the track, and we have a lever to pull the lever. The train will turn into the alternative track and only kill 1, but if we do nothing, the train will kill 5 people. So we will take the choice to pull the lever. That's the environment.
Yes. So would you pull the lever? Save 1 for the cost of 1? Save 5 lives for the cost of 1? Yeah. The thing is that if you don't pull the lever, you're not responsible for the deaths of the 5 people. Or, well, maybe by omission, but let's say. But then if you pull the lever, you killed 1 guy.
There are many outdated word.
Yes, for autonomous vehicles, but even before in medicine, there's like this idea, if you have 5 patients that need organ transplants, and if they don't get the transplant, they're about to die. And then there's another that could give them transplant and he's about to die. Would you basically sacrifice? And it's like, well, yeah, okay. But then if you change that other, basically it would be like a patient that just came with a broken leg and he would recover. And it's like, would you take his organs and kill him to save the other 5? It's like, because mathematically it's the same. But then morally, it's like you kill 1 person in one sense, and in other is, well, we're going to die anyway. Yeah. My daughter was showing me an Instagram account that has so many variations of the trolley problem.
I mean, I think many political decisions are also based on this.
Yes. And it's like this choice, damned if you do, damned if you don't. Okay, so this synthetic method, we can relate it to this quote by Richard Feynman: "What I cannot create, I do not understand." Basically, I mean, it's similar. I think it was Heidegger who said that you understand something when you are able to explain it to somebody else. So this is the idea that you really understand something when you can build it. And Hiroki Sayama on his social networks, he riffs on this phrase and he says, what I do not understand, I can still create. Because in artificial life, we can build many things. And why do they work? But we build them anyway. So, one of my advisors from my bachelor's thesis, one of the pioneers of artificial intelligence in Mexico, he used to say that the best way to understand man is by creating him. Yeah, don't mind the pronouns. He's from the old generation. And then let's say if we go more philosophical, we can ask, okay, what's reality? In sense that we try to be objective as possible. Science tries to be as objective as possible because, of course, traditionally, when there were different discussions, especially against the church, people didn't want that the truth would be tied to the opinion of someone. So it's better if truth, whatever it is independent of the observer. So that's why we try to be objective. And also in science, especially if we have this idea of a single truth, we don't want that every time we ask a question, we get a different answer. Unfortunately, there are many systems that work that way, and not only biological and social systems, even physical systems. A colleague from the same college, from Watson, Bhagat, he works with boiling water, and he was telling me that every time they boil water, the bubbling, so basically the breakage of the surface tension, occurs at different temperature. And they don't know why. And it's something that they cannot replicate. And I mean, it's not that it's subjective, it means that it's not repeatable. But then perhaps thanks to the success of physics, many people feel that only matter and energy are real. But then what are those made of? And then, well, elementary particles, but then are those real? And then we don't know. I mean, we can detect them, but we don't really have a good description or understanding of what they are. I mean, are they particles? Are they waves? Because of course we have equations that describe them, but the equations are not the real thing, just like Magritte's painting of not an apple is not an apple. And the word apple is also not an apple. But anyway, we need these descriptions of phenomena, or these models, in order to be able to speak about them. But I mean, there's this idea in philosophy, well, basically materialism, that says that only matter and energy is real, and then all the rest is epiphenomena. So a consequence of reductionism, which is the idea that we can explain all the behaviors of a system from we can reduce it to its components. So let's say, in principle, what that is saying is that if we had all the information of my elementary particles, we will be able to predict what I'm going to say next. and there's debates in favor or against that statement. I would say that's nonsense because meaning is arbitrary. And well, example I give is with money, because the value of money is not in matter or energy. Of course, there's a substrate for money. Let it be gold, let it be cacao seeds, let it be shells, let it be bits in Bitcoin. But then the value of that matter or energy, it's a social agreement. It's not an inherent aspect of that matter and energy. You can have those bits, and then those bits are erased. Or let's say if you have bills, and then there's a crisis, and the value of those bills, it's nothing. Or in many cases, you have coins which value is less than the metal itself. So, however, if money, which is not material, is not real, how did we end up with this building? You needed money, so how can you explain the transformation of matter that makes this desk, this chair, the door, lamps, from wherever it was, some forest, mine, wherever, to a processing plant, manufacturing plant, then transport it all over the world without money. So if you have a description of the matter, let's say a whole mountain, you can in principle describe, well, in practice we can't, because there's not enough time in the universe for all the possible combinations, but let's assume that you will be able to predict that. You would need to include the whole civilization in your model, so that some machines would come and start digging the mountain and take some things and then ship it to China. So some kids will work and then produce whatever, no? So anyway, and this has to do with causality, and I mean, we will speak more about causality next week. And of course, there are different understandings of what's reality. So for example, in Buddhist philosophy, if something changes, it's not real. So for example, our emotions are not real because now I'm angry and tomorrow I'm not. Or so why do we put attention to them if they're not real? And then what is real is that which doesn't change, which is different from Western philosophies. So Saraha, who was Mahashida, attributed those who believe that what appears is real are stupid as cows. Those who believe emptiness is real are even stupider. So it's like middle way. Or a French philosopher, there's no such thing as a thing. And then any opinions on what's truth? How do you define truth? It's one of these things that we take for granted, and well, that's it.
What is meaning of life?
Yeah. Do you have the answer for the meaning of life?
That's truth. Once I find it, I find truth.
Ah, okay. But then what's truth? What do you find when you realize the meaning of life? I mean, there are different approaches, lots of different theories. We could say that it's some correspondence with reality, that maybe it has to do with reproducibility, but there are also other issues with reproducibility. Because at the end, we can say that science is about finding truths or correct descriptions about our world. And by descriptions, we mean models. So what would be, or let's say, generalizations of models that would be more laws than models. But then we see that it's not something fixed. It's not something given. There's no absolute truth, because even we want it to be as objective as possible, we cannot get rid of the observer. And in philosophy, epistemology is the study of knowledge, how we know, how we can know. And of course, we want to know as much as possible, but we are limited. And there's this idea, I think we already spoke about deliberate ignorance, right? About people not wanting to know when we're speaking about taboo topics. But anyway, some people would like to be able to know without epistemology, but it's not possible, no? Because let's say there has to be an observer, and let's say Godfrey Reggio, who has done several films, maybe you saw Koyanis Tachi. He says that the metaphor is what we know. And I like to use this example of a sphere that is half white, half black, but we can only observe it from a single perspective. So actually we don't see a sphere, but a circle. So then we ask, what's the color of the circle? And then some people from their perspective, they say black, or some others say it's white, or say half and half. And of course, I mean, we can argue about what's the real color of the circle. But it's basically different descriptions of the same phenomena from different contexts. And since in daily life and in science we have different narratives for different purposes, then it's difficult to say, oh, this is the right context or the right perspective to observe a phenomenon. Because it might be, no, that, okay, there are different perspectives, but this is the right perspective, and then all the other perspectives are wrong. Well, neither, because depends on the purpose. There will be different descriptions and different perspectives that will be more appropriate. So it means that there's not a single truth. So of course, trying to be pragmatic, in some cases we might choose one perspective, in some others another perspective, but if we stick to one and deny all the others, we will be less flexible than if we accept that there's more than one perspective. And not only about circles, but about any models, and not only in science, but in everything. And ontology is the part of philosophy that studied things objectively, the beings, independent of observers. But the moment that you describe it with language, it's already becoming epistemology. So ontology at the end is epistemology and is partially subjective, because depending on the language that you speak about ontology, that's already affecting your description of reality, because supposedly ontology describes reality. But of course, epistemology also needs ontology. We cannot arbitrarily say all descriptions are correct. We need precisely this feedback to contrast our description with the described, the map with the territory. Because basically what this is telling us is that, of course, from the same territory, we can make several maps, different scales in color, we can focus on the political boundaries, which are pretty artificial. We can focus on the altitude, on the orography, on different features. So it's not that one map is true and the others are wrong. we know, no, that this is a hiking map, this is a driving map, this is a, I don't know, war map. They will all have different features and requirements. And they're about the same territory. And however, it doesn't mean that now all maps are valid. No, there should be some consistency between the map and the territory. So also epistemology needs ontology. We cannot really separate these two. So I like this quote from Schrödinger: "The world is given to me only once, not one existing and one perceived. Subject and object are only one. The barrier between them cannot be said to have broken down as a result of recent experience in the physical sciences, for this barrier does not exist." So basically what he's saying is that it's a bit artificial to have this distinction between the map and the territory because you cannot have one without the other. No? I mean, even the maps of Middle Earth, that it's like a place without territory, but it's like a territory in fantasy, and then let's say there is some correspondence to that. But anyway, this is again resonating with Buddhist philosophy, where it said that the difference between subject, object, and action is an illusion. Again, because you cannot have one without the other. Okay. Questions, complaints, political statements?
No questions.
Good. So for next class, please read one of these three. I highly recommend one of the first two, as opposed to the third one. They're much deeper and classics. So the one of Philip Anderson Morris different is like a classic about emergence. So Phil Anderson is Nobel Prize winner in physics, was, and he in this paper he clearly states what's the problem with emergence. Well, one of the problems with emergence. So it will be useful for class next week, but then we will discuss this on Thursday. And let's say living things, we can also say that they're emergent. So this would also be useful to discuss emergence. And obviously, the third one is about emergence. Those of you taking the other course 547, please don't choose the third because we will discuss that in the other class. So choose one of the other two, of the first two for sure. And the readings for next week are already on Brightspace if you want to start checking them. But yeah.
With all the assignments, will be reading and
Similar, yeah. Yeah.
are you gonna discuss the project, which talks about projects?
Yes. So I forget which week we will brainstorm about final projects, and then you will form groups, and then you will present ideas of projects, and we'll criticize them and give constructively, of course. And like that, we will go. So let me see quickly which date. So the 3rd of March, yeah, in 1 month we'll have brainstorming about projects. If you have ideas about projects, we can brainstorm before. Yes, group. How many? Yeah, I need to see how many students are online and here, and also not here. How many students are enrolled to decide on the size of the groups, but maybe about 3. The 3 people, the groups of 3. and let's say combining remote students and on-site students. Yep. And also I can suggest some projects. I have a list of projects. Okay. See you on Thursday.
See you Thursday.